Hi guys. So today we're going to be talking about lecture 10, which is going to be about functions with multiple definitions. And since it's rather late in the evening right now, I'm going to be foregoing my usual video inset. I know that you'll all miss it desperately, but I promise I'll be back next time. So we're also going to talk a little bit about an approach or several things you might think about in your approach to problem 19, which is probably the hardest question that we've seen so far in terms of thinking about how to take mathematical ideas that you already know and translate them into computer code in a way that the computer can think about. And that's the problem of anti-differentiation. Now, of course, Mathematica has its own integration software, but the point of this exercise is to think about how to translate your mathematical knowledge into a function that can act on that knowledge in code. So let's begin. So in our last section about pattern matching, we saw what the wildcard symbol was, right? This underscore that we've had underneath or next to the input of every function that we've defined. That is actually a symbol that means an expression with no limits on what that expression could be. And the name that came before it was just a name for the expression that we could use in the body of the definition of the function. So this function right here, where I have f of n is equal to 2n plus 3, the underscore here actually represents any expression that can be fed in, and we've given it a name, n. So that when I write the definition of the function, and I can have a name for the object that I want to manipulate. Now what that means, because we haven't put any restrictions on what n could be, we could evaluate things like f of cloud. And we'll see that we get 3 plus 2 times cloud. We've put no restrictions on the sort of input that we can put into f. And it turns out to be the case that we can restrict function definitions in exactly the same way that we did pattern matching. We can take one of these wildcard symbols and attach to it a condition finder that will only evaluate the function with that particular rule if the input meets that particular conditional. So n underscore means an expression of any kind that we label with n inside the function. So I could be a lot more precise about the sorts of things that I allow to be evaluated in my function. So suppose let's clear f real quick here. If we define f where we say n must be a positive integer, that is exactly what this is doing. This says, in the same way that we did this when we were doing pattern matching, I want to feed an expression in, and the type of expression that I should consider is an integer expression, and further, that integer had better pass the Boolean check that is a positive number. And in that case, then we allow f to evaluate the number. So with the function I've got written right now, if I write f of minus 2, I get minus 2. Remember, I cleared the definition of f. So f doesn't know what to do with negative 2 because negative 2 is an integer, but it's a negative integer, and f has no definition for negative integers. We can check that by writing question mark f. And you can see that f has a single definition that knows what to do when the input is a positive integer. So if we want to have a function that has multiple definitions, what we can do is define the function multiple times. If we go back up here and we run this definition of f again, that doesn't replace the definition that we just made because it's asking for different conditions on the input variable. If we go back down and run our check on what exactly f is right now, we see now that f has 2 definitions. It has one definition that accounts for general inputs, and it has a different definition that acts when the input is an integer that is a positive number. So if we evaluate f of 3, we get 12 because what's being acted in that case is this definition. However, if we evaluate f of minus 3, we get negative 3 because in that case we're doing 2 times negative 3 plus 3, which is negative 3. Okay, so 2 different definitions for the same function. And this ability to define multiple definitions for the same function is going to be very useful for having the same name apply to inputs that have different structural characteristics. So you can actually build functions that have more interesting domain restrictions. So if you want to have a function, for example, that you only want to evaluate on polynomials, so this particular polynomial is an expansion function, or this particular function is designed to expand a polynomial and do nothing to anything else. So you might wonder, what's the name doing in here? Well, we're going to be referring to that name in the body of the function, so I have to give it a name. The double underscore, if you recall, means that we're going to take in a complex object, not just a single object, but a complex object. And then the object that comes in, we evaluate to see, is it a polynomial? That's what polynomial Q tells you. If it is a polynomial, then we apply the operation expand it. So we can check and see. If I put a function like cosine of x in here, it doesn't evaluate. I have e of cosine of x. If I feed it an expression that is a polynomial expression, whether before or after multiplication, you can see that it actually does expand it. Okay. If you decided you were going to try to trick it and put a -1 up here, well, now it's not a polynomial anymore, so it quits, because there are terms in here that are not polynomial terms. Okay, remember, polynomial has to have positive powers. So the idea is that this gives us an extremely powerful way of determining how a particular function acts. You might think, how does Mathematica determine what order to apply these definitions in? So if we just define the function g and say g of x is equal to x, and if x happens to be an integer, then instead of returning x, we're going to return x factorial. If we check the number 2.1, we get out 2.1. If we check out g of cloud, of course, we get cloud, because we didn't put any restrictions on this expression up here. If we check g of 4, we get 24. So the idea is that no matter what order I define the functions in, Mathematica tries the most specific restrictions first. So it starts from the most specified function. And if the input fits the most specified functions, it evaluates on that definition. And then the sort of end state, the fail state, is if it doesn't meet any of the specialized definitions, then it evaluates on the general definition. Now, it does evaluate in order if you have lots of expressions that have complicated conditionals. And so in that case, it may matter what order the definitions are made in, although you can usually avoid that if you're clever about the way you set your conditionals up. So let's look at an example here. This is one called this is the core of a function called the Collatz function. So the Collatz function is a function that counts how many iterations it takes for a number to get back to 1 by repeated application of the function f. So this is the core function. That is not the Collatz function, it's the function that's used to drive the Collatz function. So the core function is f of x is equal to x over 2 if x is even, and 3x plus 1 if x is odd. And so we're not going to use if to set this up, we're going to use multiple definitions instead. So we'll start, maybe not with Collatz here, we'll start with f. And we've got a definition that says if x is an even integer, then we are going to spit out x over 2. If x is an integer, we get 3x plus 1. Why do we not care about putting odd q in here? Well, the only thing that's left over when we're done evaluating for evens, if it doesn't pass that condition and it's an integer, then it will be an odd integer. So I don't actually need to specify in that case. So I can check when I evaluate these things that it says f of 3 is 10. Of course, that's because 3 is odd. 3 times 3 is 9 plus 1 is 10. We can check on another odd number if we like, just to verify that we've got this set up correctly. 16, because 3 times 5 is 15 plus 1 is 16. And if I check any even number, then I'm getting out the number divided by 2. So to build the Collatz function is actually to take this particular set and apply it over and over and over again to a number. And so you could do something like nest or nest list on these functions and apply f repeatedly to a single number. So for example, you could nest while list. We're going to apply the function f. We're going to apply it to, say, I don't know, the number 240. and we will apply it as long as the output is bigger than 1. Let's see what it spits out. Okay, so this is what the Collatz function does, right? It applies f repeatedly. And notice that the behavior of f is precisely what we expect from our multiple definition. Every time we have an even number and we apply f with a single name f, every time I apply f and the input was even, we halved it. But every time I applied f and the input was odd, I tripled it and added 1. Then halve it, then triple it and add 1. And so the length of this list that is the output of the Collatz function. So the Collatz function would say that it would assign to the number 240 the value 22 because it took 22 steps for f to produce the number 1. Okay? The Collatz conjecture is that every number converges to 1. That's not a proved property yet. But this is the idea, is that a single name can give you multiple behaviors, even in something like a nest type setup or repeated composition. So now let's talk about local variables and modules. We've already talked a bit about basic ways to create a function with several lines. So the most straightforward way of doing that is to separate your lines that you want to execute with a semicolon and then wrap the entire thing in parentheses, and what you'll end up with is a function that has multiple lines. There's a formal way of constructing these sort of objects. Instead of the informal way of surrounding with parentheses, we can use an object called a module, which actually allows us to initialize and use what are called local variables that only act within the module structure. And that gives us kind of something that looks like more like the sort of structure you'd see a procedure, for example, in a C-based language or in Python, where you have bricks of code that operate all together and with their own internal variables that don't interact with the outside variables until the end of the question, or until the end of the operation of the function. So as an example here, we're going to write a function that say finds all the primes less than an input n. So in the following function, we have variables pset and I. So these variables right here in the language of a module, those are local variables. So we can call these guys right here, these are local variables. And so that means that they are not defined outside of the body of this function. They can't be interacted with. They're not accidentally going to be overwritten by something else. The function has variables that it's protected, that runs internally. Now, you can still feed numbers in from the outside through the input. So we've got this input here where we're going to take in some input. Of course, if we're finding primes less than an input n, probably we want this to be an integer. We're just putting that in there as a reminder that we can restrict the domain of the functions that we're working on. And now what do? Well, within the wrapping of the module, we can use as many lines as we want. So the first thing we run is a while loop. And it's pretty easy to see what the while loop is doing here. While the ith prime is less than the number n, then your prime set is your previous prime set unioned with the current prime. And then you just increase the index by 1. So notice you have this internal index I. This I equals 1 right here is an internal index. And we increment that I, but the p set, for now, the particular p set that we're stating at the end here, that is the output of L primes. So that's stored internally, and the reason that we say it at the end all by itself on a line is so that L primes actually produces an output that's visible to the outside world. If we took this out and ran the function, nothing would come out because all of the variables are defined internally. So somehow when we're setting up a module, we need to make sure that we produce something that can be spit back out again so that the function is useful. And you can see if you evaluate this thing that you get the typical. We've done this function before a couple of different ways, but this is the first time that we've been able to do it kind of all together as one function instead of a bunch of broken apart lines. So modules are a really good way of organizing your code, particularly if you are the sort of person who finds yourself having 8 or 9 different named functions and you're stitching them all together into some crazy brick by the time that you're done. Think about using modules to arrange your thoughts. Okay. The last thing I want to talk about is what on earth is going on problem 19 and how you can think about approaching a problem like constructing antiderivative functions using the ideas that we've seen so far. What the problem asks you to do is to write down a function antiderivative. An antiderivative should have the property that it can distinguish between polynomials and exponentials with positive base, and also x to negative powers as well. So there's actually 3 different things that we want to be able to differentiate. We want to be able to handle polynomials. We want to be able to handle exponentials with positive base. And we want to be able to handle x to the negative. Okay, so that's sort of 3 basic cases of calculus. So before we leap in and start writing this function, the first thing we might try to think about is, how do you integrate a function without using the integrate feature? Of course, Mathematica has one. We can always use it to verify. You know, we could integrate x squared with respect to x, and it will tell us that it's x to the 3rd over 3. So the point is that we don't get to use the integrate function for what we're working on here. We want to make a function that does that has the same inputs. It takes in some kind of expression and some kind of variable, and it integrates it. So we want to reproduce this in the special cases, right? Polynomials, exponentials, x to the negatives, and linear combinations of those guys, so things that are connected with plus. So the first thing you might think is, okay, let's handle the easiest possible case first. Okay. Now there's a lot of ways that you can approach thinking about polynomials. A polynomial is just a list of coefficients, for example. But my idea when I look at this function, or this problem, is I think that I want to break it down and work term by term. I don't want to deal with complex operations. I want to try to integrate x to the 3rd. That's my goal. I want to integrate x to the 3rd, because if I can integrate x to the 3rd, I can integrate x to the 4th, 5th, 6th, or whatever. I can deal with monomial terms, right? Monomial terms from polynomials. So one trick that we can use to tell if a monomial is a polynomial term is we can use the query polynomial q. Is x a polynomial? Well, we have to say in x. Yeah, x is a polynomial in x. Is x squared a polynomial in x? Yep. Is x to the -1 a polynomial in x? No. Okay. So polynomial q will tell us if we have something of the form x to the n. And that matters because there are some cases where you can't read off an exponent. So an x all by itself doesn't have an exponent, so you can't use pattern matching to take care of that case. So let's use polynomial q to set up and integrate a function that will integrate for us. And the first thing that we're going to do is we're going to construct all of this inside of a which structure, because ultimately I want this function to be able to tell the difference between polynomial terms or monomials and exponentials, or x to the negative powers as well. And so I'm going to start from the beginning by building it into a which structure. So let's call this function int. So we're going to integrate with respect to a term and some variable x. And we want it to be the case that whenever the input is a polynomial, and in particular a monomial term, and I'll show you guys how to make sure that it's a monomial term in a second. Let's suppose that we check to see that our polynomial term, polynomial q, that's the true statement, that the thing that we're looking at is a polynomial in x. If that is the case, then what I would like to do is I would like to take the thing that came in, that monomial term that came in, and I would like to multiply it by x, and then I would like to divide by the exponent of the new object. All right, well, let's see what it does. So let's integrate x to the third with respect to x. Oh, sweet. X to the fourth over 4, that looks right. I could get cute if I wanted and put a plus c on the end of it. But this is precisely what we wanted this function to do. Okay. Does that work for x to the fifth? Yes. Does it work for x to the minus 2? No. Nothing happens in that case because x to the minus 2 is not a polynomial, and so that is not considered by the which structure that I've used here. Now, this approach I'm taking does not involve multiple definitions of a function, but it's very easy to take this which structure and to move it over into multiple definitions. And so this is kind of the beginning of thinking about how to do this, is just to figure out how to do it on single terms. Okay. Now, how do I guarantee that if I get a complicated set of objects that I can work term by term? Well, if you look at the examples that are set up in the homework, if you have something like x squared plus e to the x, let's do actual e here, e to the x plus, I don't know, x, 7x to the 7th, if I try to feed that into the integration here, I'm not going to see that it's a polynomial. And in fact, different operations need to happen on different pieces of this. So the trick is, if you don't want to have to deal with that thing as a combined list with plus, just like on the exam, you could take this and you could apply the list head to it. And that's going to turn your list of things that are connected together with the plus sign into an actual list of objects. And now, whatever function we're defining here could be applied term by term to that list. So the idea is that if we can define a single term antiderivative, we can map it onto the list of input terms. And then when we're finished, we could go back and we could just change the head back to plus again and get a function out the other side. Okay. So the trick is, this is a trick to make sure that you always can work one term at a time. So this allows working term by term. And this sort of is where you should start thinking about how to define these things. So there's some special cases that you need to worry about. So for example, you need to worry about the case x to the minus 1 because it's a separate case. And so when you're thinking about how to continue this process, what you should think is, how can I make this thing find cases of x to the minus 1? And this is a perfect setup for something like match q. And the pattern finding that we did in the previous section should guide your approach to this which structure, or to setting up multiple definitions of whatever your anti-differentiation function is. Okay? Because that pattern match is going to tell you how to set up which particular definition is being applied. So what I want to put in here is a pattern that matches x to the minus 1. How do I find x to the minus 1? And when I do, it must integrate to log. So I've got to do something with log. It has to return log here. Okay. All right. So I think this is a good place to start with this. I'm going to take this line out. I'm just going to comment this line out so that it doesn't bog the software down. Let me get rid of this. This is the core idea in building up a function that can distinguish between polynomials, considered term by term, exponentials with positive base, which have a different rule. And that's actually sort of complicated because one thing that you have to do if you want to integrate those in the sort of way we've done here is you have to be able to extract what the base is, because the integration rule for exponentials is the integral of a to the x is equal to log a times a to the x. And so I have to be able to extract the a. And in that case, so here's another hint. If you had something look like 2 to the x and you full form it, you should notice that you've got power as the head. And the objects inside of power can't be dealt with indices, but the base is in position 1. So a way of getting into the bits and pieces that construct an exponential is actually to use the same trick that we used on the polynomials. You can apply list to this. And what that does is it strips the power head and replaces it with list. And now you can get the base of an exponential out just by looking in that first slot. And this trick is really useful for pulling out, at least this is the way I came up with, for pulling out the base of an exponential, of a generic exponential with positive base. So I have complete solution to this written up. If you have questions about your particular approach or how you could make things work more efficiently, I would ask you to ask me. But I really want you to think hard about this question, because it's an excellent question for thinking about how to take an idea of, or these rules that we learned in mathematics and put them into code. So it's not the case that we're going to be running around using our own anti-differentiation functions, but it is the case that the translation process is like the core of mathematical programming. And I'm really looking forward to seeing your efforts on the antiderivative problem. So I hope you enjoyed these questions, and I will see you guys, my smiling face in the corner of the video, for lecture 11. All right, good night.